Hello. I am going to share with you guys how to do the Excel for a Runge-Kutta, which is a kind of the standard numerical solver for differential equations. And so to kind of get started, let's just remind ourselves how we did the improved Euler's method. We had kind of the column for t with your time step right here. Your initial value is going to go right here. And then my columns are kind of what is the x value at that given t. So what's the function value? Our initial slope, which is depending on the differential equation, just plugging in the initial time and initial x value. And then tilde x is kind of following our x slope, our Euler slope for one time step. And then the idea is that we want to compute the slope at the next time step, and that's what this is. So that's M1. So M1 is kind of following the Euler slope, and then you plug in the time step at that when you went a one time step, and you plug in the x value, which we just computed over here, which is we call it tilde x, which is just x evaluated at the next time step. That gives us a new slope. And then m is just the average of those two slopes. You take the average of those two slopes and that gives you m. And so then our new kind of value is we're going to, and so this is not labeled the best, but we're going to take the point we started at, and then we're going to add delta t times this slope. And that will give us our value. And so that's how you do an improved Euler's method. And so now we're going to improve it even more, and we're going to do it what's called Runge-Kutta. And so we're going to have the same kind of idea here. I'll still have a delta t time step. So this is my time step. For our problem in the exam, we start with 0.5. My initial condition, so x of 0. We'll call that, I think it's 1 in the problem. And then same columns, we'll start with a t. We'll start with x of t, so that's the value. And so for us, we'll start at 0, we'll start at 1. The next column, according to the algorithm, is we need to compute m1. So m sub 1 is going to be equal to, it is just our slope, so x prime, and then evaluated at the first point. And so t and x, I think that's fine. And so if we're doing t minus x, this will be t minus x. And so that's our approximation or a slope at that starting point. Um, that's m1. M2, slightly more complicated, but it's going to be the function, so x prime evaluated at t plus a half a delta t. So I wish I had a good letter for that, but the time step, delta t, and then divided by 2. So we want to do half a time step. And so that's where the t value is going to come from. And then the x value is going to be following this slope m1, and we're going to follow it for half a time step plus our original point. So it's x plus m1 times delta t over 2. There's this looks horrible, but that's the idea. And so coding it is maybe the better thing. And so what would that be for us? So our differential equation is t minus x. And so for t, it's t plus delta t. So it's going to be this value plus our delta t value. And because delta t is not going to change, I'm going to put dollar signs on that. Whereas the t is going to change, but delta t is not changing, and then divided by 2. And then, so that's the t value, and then I need to subtract the x value. The x value at this point is going to be our starting x value, but then we need to follow the slope m1 times delta t. And so you're going to do plus delta t, and again, for that, we need to put dollar signs on. Whoops, did not mean to do that. Maybe I'll just do it like that, times, and it's delta t over 2 times m1. I think that should do it. Let me put dollar signs on there. And then I don't think you need parentheses. I mean, the order of operations should be fine, but just in case. And so this is M2. So it's are we plug in t plus delta t over 2, comma m plus or x plus m1 times delta t times 2. Plug that in for x, plug that in for t, and that gives us that value. And I think that checks out because the delta t step, so it'd be 0 plus 0.25 minus x is 1. Following the slope for half is going to be uh negative zero point 0.5. And so if I do, is that right? It should be the t value minus the x value when we follow the x value a little bit, half a time step. And the x value, if you follow it at half a time step, should be you take this value plus half zero point 0.5 of that value. So that should be 0.5. And so I do the t value minus 0.5. I think it should be minus 0.25. Does this need to be in parentheses? I'm a little bit concerned. Hmm. T. So I take the t value plus that over 2 is 0.25 minus the x value plus 0.25 times the slope. Oh, it's 0.25. Oh, that's right. Okay. And so that's why it's going to be negative 0.25. So it's minus 0.75. Okay, no, this is right. This is right. Okay, so that's M2. Sorry, yeah. Now we're back on track. Let's move this over. So that's M2. M3 is gotten much the same, but we follow instead of M2 or M1, we follow M2. So M3 is almost exactly the same as this. Um, so Command C, and that will go here. The only difference is that instead of an M1 here, it gets an M2. And so the formula is very, very similar. And so what we're going to do is we're going to take this new slope we just got to get to kind of compute this node one. And so we need t plus delta t. So that's going to be the same. So actually a lot of what's here can be repeated almost verbatim. So I don't know what I just did, but I don't want to do that. I have to undo that. That's the thing I don't like about Excel is that if you press the wrong button, weird stuff happens. So I need to Command C that, Command V. Okay, but I need to change the values that need to change. So the t value, it took the wrong thing. This should be O. So that should be the t value plus that. That's good. And then I want to do plus the x value, which is still p. So that's p. Plus delta t is still over 2 is still that times uh, R4. Actually, that is correct. And so I believe that is our M3. Great. So we have our third slope of the 4. Now the final one is M4. And M4 is you follow M3 for a full step. So M4 is going to be equal to you plug in t plus delta t. So t plus delta t over, not over 2 actually. This one's going to be the full one. And then you're going to do x plus M3 times delta t. I wish there's a better way to label these things. If I wasn't uh if I had more time, maybe I would, but for our purpose, this is fine. Anyways, so what's this going to be? Our t is this value plus delta t is that value. And again, because that one's not going to change, I'm going to put, oof, I hate when that happens. Okay. Plus, or sorry, minus. So dollar signs on that. And then minus, and now I have to do x plus M3 delta t, where x is where we're starting at. and then plus M3. M3 is that value dot delta t. And again, oops, I need to put it here. Dollar sign on that. And then that should give us the approximation of the slope at the end. And that's our M4. And so now we have one, two, three, four slopes all computed. This was the Euler slope. This was kind of following a half step of the slope and following a half step of the next slope. And then this one is following a full step of this third. And so it's kind of you keep uh, doing new slopes based on the old ones. And then finally, what is M? So M, the slope that we're actually going to use is a combination of M1, M2, M3, and M4, and it's a weighted average. And so it's going to be 1/6, so sorry, equal 1/6. Is that how I want to do it? Yes, it's a weighted average of that. And so times, and then parentheses, you're going to do M1 plus 2 of the M2s. Whoops. Okay, plus 2 times M2 plus 2 times M3 and then plus M4. And so it kind of gives one weight to M1, two weights to M2, and two weights to M3, and one weight to M4. And so this is the weighted average of that. And it gets you this kind of slope that's an average of these slopes that's trying to capture a lot of things. And now finally we get our next point. So x of t plus delta t, like the actual next point. And how do we get it? It's we follow this slope. And so it's going to be equal to where we started, x, and then plus this new slope times our delta t right here. And then to make sure that it's fixed, we're going to put that in dollar signs. And so we get to 0.7, and now we can do it all over again. What's this one going to be? This one's going to be equal to that one plus that guy. And again, we want to put that in dollar signs because the delta t is not changing. What's this new x value? This is where the Excel comes in. We're going to make it equal to that cell. That goes there. Great. And now this formula, I believe we can just drag down and it should be fine because it's just the difference of those two. That's great. This formula hopefully also should just be able to drag down and should be work because it should be the new time value, which is that plus that over 2 minus the new x value, which comes from this slope times delta t over 2 times that point. So that looks good. And so we should be able to drag actually each one of these down. I like to do it one at a time, just kind of make sure. Whoops. Drag that down one. Looks good. Drag that down one. Looks good. And then so the m is the weighted average of those. And then we get a new x value. Okay. And so now I can take this whole line because this second line now has all the data I need, and I can drag it down. And at t equals 2, I get 1.27 is the value there. And so I don't know what the actual value is. Um, I should probably figure out what the actual value is. But what did Euler's method say? Let's see how far off this is from Euler's method. For Euler's method, I have to change the differential equation. Which differential equation is this? This is t plus x. If I did t minus x and then change that, that's good. That's good. That's good. So this needs to be minus, minus. And then if I follow this down, oh, my initial condition is not good. Like that one. And at 2, I get 1.77. Are these correct slopes? It's just the difference in those slopes, and then this is just, no. So it gets 1.77 when I do a delta t of 0.1 for that differential equation with initial condition. Whereas over here with my Runge-Kutta, I got 1.27. So if I change my delta t to 0.1, and then drag this out, Let's see. See what happens when I go to 2 here. 2, 1.27. So pretty good. Whereas if I do my Euler method and get this to point like 0, 1, let's see if that can get where I want it to go. Uh, it's actually it's even more off. Hmm. Is this correct? Minus. Oh, I have the wrong things being subtracted. That's why. It should be t minus x. I was like, this is not even close. So it should be t minus x. Okay. Let me drag that and see how that does. Here we go. 1.267. That looks a lot better. Okay. And so that's with point zero 0.01, whereas with point 1, with point 1, how accurate is it? It only gets to 1.24, so it's actually not that far off. But then at point 0.01, it gets all the way up to 1.267. So the Runge-Kutta did that using where is it? The Runge-Kutta one can do that accuracy with even using step size zero point 0.5. It can beat that accuracy. I think the actual value is something around 1.27. So yeah, so that's the idea, is that you kind of build the slopes M1, M2, M3, M4 to kind of make a new weighted slope that you're going to follow. And then that gets you to the next point. You just keep doing it. And so you could do this with different differential equations, but this is what we wanted to do for this problem. So that's how you build Runge-Kutta, and so you can play with it with other ones, but that's the idea. All right. Well, have a good one, guys. I'll see you.